Hello everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In last class, we started our discussion on FETs. We already discussed the differences between BJT and FETs. Now in today's class, we will elaborate the topic junction field effect transistors or JFET little more. So let us begin with the class. JFETs. JFETs are nothing but junction field effect transistors. So there are two type of JFETs. One is N channel and second one is P channel. If I talk about the construction of N channel JFET, so we have the doped silicon wafer or any semiconductor material which is doped with N type impurities, and similarly doping of two P type well also there. So this is P and this is P type of impurity. So one wafer which is fully N type of impurity doped are further doped with P type impurities in a well structured manner. And there are three terminals. First one is drain, second one is gate, and third one is source. And this current flow in this is, which is ID, flow from drain to source. Okay, so this is the flow of current, direction of current, which is drain to source. Now here, this thing between these two P wells and drain to source, this thing we consider as channel, because current is flowing in this manner, so current is flowing through this channel. So this is considered as, so this is the basic diagram, and we will make the impurity well here. So if this is N channel, so here are P type of impurities. We are discussing the working of N channel. So this is our gate terminal, this is our drain, and this is our source. So in fact, the current always flow from drain to source. Okay, so this is the flow of current, direction of flow of current from drain to source. Now here the impurity is N type, so N channel. Here we have to make the metallic contact also. So these are the metallic contacts, and these two terminals are connected with each other. Okay, so this is the basic diagram of N channel JFET. Now here, if I talk about the construction first, then we have to consider one thing here. This is N and this is P. So in PN junction, a depletion region form. Okay, in every PN junction, a depletion region form. It doesn't matter if voltage is connected or not. Every time when PN junction is formed, a depletion region is also formed. So this is the depletion region. Okay, depletion region is a region where no free charge carrier are there. So many time in BJT class I already discussed. You can check the class from here. So this is the depletion region. And from earlier classes, we know that the thickness of the depletion region is depend on the biasing voltage. Okay, if we increase the voltage, the layer behave like different, and if we decrease the voltage, the layer thickness behave like different. So if we increase the voltage, the thickness is higher, and the reverse bias. If we increase the reverse bias voltage, then the thickness is higher. If we increase lower the reverse bias voltage, then the thickness is less. Okay. So, remembering these fundamental, phenomena, we will discuss the working of that. In between this drain to source, this we consider as channel because current is flowing here. So, this is the channel where current is flowing. Now, if I talk about the working, we have two cases. First one, when VGS, this VGS, okay, voltage between gate to source is 0. And the second one, when this VGS is negative. Okay. Now, why we are considering VGS only? Because in earlier class also we studied that the output current ID is function of VGS, which is gate to source voltage. Okay, it is a function of VGS. Now, if it is output current is function of voltage, then it is a voltage control device. We know that FETs are voltage control device or JFETs are voltage control device. Okay, so this is a voltage control device. Now BJT current control device, we know that in BJT, what is happening in BJT? I hope you remember. IC, the output current is the function of beta IB, beta time IB. So this is the collector current and base current relationship. So IC current is depend on the base current. So it means it is BJT is a current control device. Output current is depend on the input current. Similarly here ID is depend on the VGS or the function of voltage between potential difference between VGS gate to source. So it is a voltage control device. So this is the very basic knowledge of N channel JFET. Now we will discuss the first case where the VGS is 0. Okay, type of diffuser. Now if this VGS is 0, so what will happen? We have to make these gate and source are grounded with each other. Okay, these two are grounded with each other. So then this is at 0 volt. So the potential is 0 volt. Okay, P, P. So here also 0 volt and 0 volt. Now here we have to connect a battery in that manner between drain to source so that the current will flow from drain to source. If current is flowing in that direction, current is flowing that direction, it means this thing we have to consider. The drain we have to connect it with positive terminal and source we have to connect it with negative terminal. This is the basic formula. Electron flow in this direction, so current flow in this direction. Electron flow from negative potential to positive potential. This is the flow of electron, and current flow in opposite direction of electron flow, so current will flow in this direction. So this is the biasing battery, we consider it as VDB. Okay, and this is the potential between drain to source, we consider this as VDS. Okay, now here we already discussed that there are what is there? There is a depletion region. So if this voltage is not applied here, VDD is not applied, so this the formation of the depletion region is same in every everywhere. So formation of depletion region is here and it is same everywhere. But if we apply some voltage here, let's suppose VDD is 5 volt. Okay, so what will happen here? Now this is 0 volt, this is 0 volt, so here 5 volt. Okay, plus 5 volt. If this 5 volt has to travel between this channel and this 5 volt has to become 0 volt here, because this is 0 volt, so it will not directly come to 0 volt, it will gradually decrease. So somewhere it is 4 volt, somewhere it is 3 volt, and somewhere 2, somewhere 1, and finally 0. So now when the potential difference is there, so the thickness of the thickness of this junction, this PN junction will change. So this is 0 volt, this is 5 volt. It means this side N is in higher potential, so the width of this region is increased. Now if this is 4 volt, the width will little decrease than earlier. Now if it's 3 volt, further it will decrease. If it is 2 volt, decrease, and in 1 volt it will thin like that. So here the depletion region is wide, 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 and here the depletion region will gradually decrease like that. Okay, so we consider like that. The structure will made like that. Here the depletion region thickness is high and here the thickness is less. So we consider this like that. Similarly here also what will happen in the second PN junction also, here due to this 5 volt and 0 volt, here the thickness is high, more, thickness is more, and here the thickness will less. So we will remove that equal formation. Okay, so the thickness will less here. So this is the basic structure where we can see that two PN junction have depletion region formed. Okay, so this is the here. So what is happening? If we increase this 5 volt much, let's say 8 volt, so what will happen? This layer will increase more, this also increase more. If 10 volt, then more. If we increase this higher, like suppose 15 volt, what will happen? These these two depletion region will, try to touch each other, but they will not. Why so? Why they will not? Because here the electrostatic repulsion will work. Electrostatic repulsion. Sometimes in objective questions it is asked, if the layers, the reverse voltage is increased, the layer of depletion region will touch each other or mix with each other. So the answer is no. Why so? Because it has some electrostatic repulsion. What is electrostatic repulsion? Electrostatic repulsion, we can simply understand that if PN junction formed in earlier classes also, I teach you that few positive and negative charge layer is made here. Okay, positive negative charge layer is made here. So in this area the positive charge and negative charge will repel each other. Okay, same charge. So here positive connected, here also positive connected, negative connected, negative connected. So these equal charge will you know attract each other and few are repel each other. So in this case, the process of recombination due to the process of charge carriers, this electrostatic repulsion, because this positive and this negative charge, what is happening here? More positive charge, more positive charge, more positive charge. Here more negative charge, more negative charge, more negative charge. So here very strong barrier is created. So these two layers will not mix with each other because here the electrostatic charge repulsion is very much high. But what is happening? If we increase this voltage very high, very high, let's suppose beyond the limit of this device. So what will happen? We know that 2 phenol. Okay, so what will happen? This channel break and junction breakdown will occur. We know that avalanche and Zener breakdown will work in that case. Now we will discuss the current operation. You know, what is the graph between current? So output current is ID, and here we will plot graph between ID and VDD. So this is here ID and this is the VDD. Okay. What will happen when we increase this voltage? Okay. So current will increase, and at few level when this beyond this, the current will not increase but it saturate or flow in a particular manner. So this we call pinch off voltage. After that the current will not increase but current is saturate. Okay, and once this saturation has limit of this saturation occur. So when the breakdown voltage, when the junction is not able to handle so much charge, then breakdown occur and this current will increase exponentially. The junction is break and the current is increase exponentially. So this is our breakdown voltage. So this is the basic diagram of the current and the voltage graph of this FET. So in this case, we consider first case where this VGS potential is 0 volt and we are increasing the VDD. So what is happening when we are increasing the VDD? The channel width here is changing according to the voltage applied, and due to this the ID current will change. Okay, what happened? If we increase the voltage, current will increase according to V is equal to IR, V is proportional to I. So if we increase the voltage, current will increase, but in semiconductor it is not. So when we increase VDD, it is not necessarily ID will increase. What will happen? If we increase the VDD, this width will increase. If this width will increase, then resistance over this path, this channel, okay, resistance here will increase. If resistance in this channel is increasing, it means ID is not necessarily increase. ID will decrease. Okay, so ID will decrease. Now this is the basic understanding of what is happening inside the N channel JFET. We will discuss the next criteria where the VGS voltage is more negative. In this case, it was 0 volt, but in next case, it is more negative or negative. So, we will consider the case in our next class. For today, this is much. Thank you so much.